Okay, I don't know what typically you use, guys, for the length of the interaction, but okay, I introduce Bing. Okay, Bing is a research assistant in ETS since almost 1 year now. He's working with me and Ismail, especially. He's working in different fields or different topics like image segmentation, image calibration, and this work. So he's gonna show you today this work that it's still under submission at CVPR. So hopefully, if we cross fingers, we might have accepted because we got very good scores, but we'll see. So I let Bing to start the work, and I hope you enjoy it.
Okay, thanks for the introduction. So the work I present today is the work we recently done for network calibration. The title is "The Devil is in the Margin: Margin-based label smoothing for network calibration." It's a joint work with Ismail and Yun and Jose. So the topic is about calibration. So the first question is, what is calibration? Calibration is actually a measure of model's confidence in its prediction. Let's see this example. If we input an image to the deep neural networks, it will usually give two information. The first one is the predicted label, which is a dog in this case. And the second one, it will also give us a light score. It's called confidence or probability. So usually in the literature, we only focus on the accuracy, and we use some metrics like accuracy or precision or recall to measure it. And we did a lot of great work to improve the accuracy to very high. But in most cases, we omit the performance of the calibration, which is a measure for the confidence, for the distribution of the probability. So if a model is perfectly calibrated, it means that the output confidence is equal to accuracy in average. And for poorly calibrated models, there are two cases. The first one is named overconfidence. It means that the output confidence is larger than its actual accuracy of the model in general. And for the underconfidence, it's the vice versa. The confidence is lower than accuracy. It's obviously that a poorly calibrated model is not good for practical use. We want a model to be close to a perfectly calibrated. So to quantize the calibration performance, we usually use this matrix named expected calibration error, denoted as ECE. For a trained model, we can get this reliability diagram by plot its accuracy versus its confidence. So for perfectly calibrated models, which means that accuracy is equal to confidence, the curve is almost actually exactly the diagonal line, the dashed red line. And usually the real model's line is almost like this one. So if we can realize the performance by seeing the divergence between the line of the model and the ideal line. So to compute the matrix, we usually group the samples into the equally spaced bins. And then we can compute the accuracy and the confidence for the samples in each bin. And then we do a weighted average to get the ECE. For a calibrated calibration, it means that the ECE is equal to 0. So for this matrix, the lower the better. So calibration is very important for practical deployment of machine learning models. Let's see these examples. So the first example, we can see the weather forecast. So I think everyone needs to check the weather these days, and the probability is almost as important as the predicted label. So we not only need the information of whether it's rain or not, but also we need to check the probability of the rain. So different probabilities is also important for us to schedule our activity. For other applications that is highly security sensitive, we also need the model can give us actual confidence, reliable confidence, because also in these systems, a model is usually just part of a larger systems. So the downstream actions actually need the confidence to decide its decisions, and it's not good to get an overconfident or underconfident score. So that's why this topic is very hot recently, and we have a big problem for the model neural networks because there are some literatures reviews that the DNNs are very poorly calibrated. There are two possible reasons. The first one is the objective of the cross-entropy, because in the cross-entropy, it tries to push the predictions to match the hard ground truth. So even if the sample is correctly classified, it still want to push the probability of the right class to 1 with the rest to 0. And also the high capacity of the networks can let the model be very easy to overfitting on the cross-entropy object. So we can see this curve, the NLL represents the negative log likelihood. It can be also used as a matrix for the calibration. So we can see when the model is still becoming better at the test errors, it becomes worse for the calibration. So it means that it becomes overfit for the calibration matrix. And here on the right, it's the reliability of the model trained by cross-entropy. You see that the score is generally be much greater than the expected score, and then its real accuracy. So because this topic is actually very hot in recent years, so there are already some solutions. There are two families for this of the solution. The first one is called the post-processing method. It's a simple method, but it's effective to improve the calibration. It actually adds a post-process phrase to a trained model. So it doesn't need any actual training, but it needs a validation set to tune the temperature parameters. This method is working well, but it's highly sensitive to the validation set, and it cannot handle the situation of out of distribution, or called domain shift. Another family of methods is called model-based method. In this method, it tries to improve the training objective. For example, for the first one, it tries to penalize the prediction by maximizing its entropy. And the second two are label smoothing, focal loss. They are all very well-known losses, and there are two recent papers found that they are very effective for improving the calibration as well. And here is our contributions. Here we find that actually all the three popular model-based methods are connected, and they are very similar. So we will provide a unifying perspective for previous calibration losses, and they approximately embed a very similar equality constraint that they try to push the logic distance to 0. In other words, they try to push the logic output logic for all classes to be equal. And we will reveal that these constraints are trivial or non-informative. And then we motivated by this finding and propose a much simple and flexible generalization, and it can give us a more reasonable optimization goal. And also we will show some comprehensive experimental studies over a variety of applications to evaluate our method. So here, let's see some formulation first. With the DNA networks, it usually it will output a logit in the logit layer. It will output the logits for each input, and then we apply a softmax functions to make it the output to be look like a probability distribution. And then for training the neural networks, we usually the standard way is using the cross-entropy. In the formulation of the cross-entropy, the target vector y is 1 for the red class, with the rest to be 0. So the global minimum of the cross-entropy is that we predict every training samples to the softmax prediction of every training samples to be 1 on the right class node, with others to be 0. So from this sense, it's the model is overfitting. It tends to become a little overconfident. So in this paper, we also define a new concept named logit distance. It's actually a vector of a distance vector between the winner class to the rest. So it can be strictly get by the logit layer. So here our finding or perspective of the previous calibration losses. We can rewrite the 3 previously calibration loss by this formula. It's not very hard to get this. We can just get it by the expression, by rewriting the expressions, and we can find that for the label smoothing, it actually add an additional KL term between the uniform distribution and the softmax predictions. And for the focal loss, and it approximately add additional term that is negative entropy of the predictions. So intuitively, let's look at this term. The KL term reaches its minimum when the prediction just matches the uniform distribution, which means that the score for every class is equal to each other. For example, there are 10 classes. The prediction score for each class should be 0.5 if it reaches the minimum solution of the KL term. And it's the similar situation for the negative entropy of the predictions. It reaches its global minimum if the predictions just matches the uniform distribution. And on the logit term, it means that they push the logit values to be equal to each other. And it also means that it approximately imposes soft penalties for the equality constraint, because this additional term tries to let the model to be close to this constraint. Look at this one, because from this side, all the losses are connected, and they approximately embed similar soft penalties for the same hard equality constraint. Here we need to review the concept of soft penalty functions. Soft penalty function is actually a technique. It's an optimization technique to tackle hard equality or inequality constraints. we usually use it to transfer a constraint optimization problem into an unconstrained optimization problem, which can be much more friendly for the optimizer. And the penalty is the penalty function should satisfy these two conditions. The first one, it should be continuously and differentiable function. And the second one, it should be reaching the minimum when the constraint is satisfied. So here we have here from this side we argue that all these terms are actually the soft penalty for this constraint. This constraint is that it tries to let the logic distance to be equal to 0, which also means that it tries to let the logic to be equal to each other. So let's look at more details. So for the label smoothing, here is the original formula, and it's very straightforward to rewrite it into this one. We can see that what label smoothing does is add this additional term, and we have this proposition. In this proposition, we prove that a linear penalty for the constraint of the logic distance equals to 0 is bounded from above and below by the KL divergence between the uniform distribution and the softmax predictions. Let's see this one. So this proposition from based on this proposition, we can say that this KL term is equal to is approximately equal to linear penalty for this constraint of logic distance to 0. So this proposition can be proved by the expression of the softmax and the KL divergence, alongside with the property of the log sum exponential. If you are interested in the proof, you can refer to our paper for details. And for the focal loss and the ECP, it's kind of the very similar case, because we can see that the focal loss, what the focal loss does, it actually adds a negative entropy of softmax predictions to the standard cross-entropy. And we know it's also straightforward to get the insight that the negative entropy is equal to the KL term between the softmax prediction and the uniform distribution. So it's actually a reversed KL term of what imposed by label smoothing. So the proposition 1 is also the conclusion from proposition 1 is also holds for the focal loss. So now we have the insight that all the popular losses of the calibrations actually are soft penalty for this constraint. But here we have we get to the issue. We get to the issue of it. We know that the meaning of this constraint is that it lets the prediction of the probability of each class to be equal to each other. So this constraint is actually a trivial one. It's non-informative because it prefers all the logics to be equal. It kind of works because it can be acted as a trade-off term for the cross-entropy, but it's not very informative term, and we think it can limit the model to reach the best compromise between the discrimination performance and the calibration performance. And so motivated by this, we propose our solution. We generalize this previous loss with positive margin M, and here we replace the constraint, the inequality constraint to this inequality one. Here, what we want to is that we only need to penalty those logits where the logit distance is above the margin. So I think it's not makes sense to penalty the distance that is not too large. So we only need to penalty the logits where the distance is above the margin. And this is a much more reasonable and informative optimization goal. So we can guarantee that it always optimizes towards an informative goal. And let's look at this this figure. So on the left, it shows the situation for the equality penalty. And here on the right is our improved solution. So in our case, we only penalty the logits where the value is larger than a particular margin, which makes more sense and we will show that it's not. We will show that for the left solutions, it's much more sensitive to the choice of the balancing weight, and for our method, it's kind of robust to all the hyperparameters we introduced. And here is our solution. Here is the constraint optimization for the calibration. So we minimize the cross-entropy with the constraints of logit distance equal or smaller than a particular positive margin. And in our implementation, we resort to a very simple unconstrained optimization by the nonlinear ReLU functions. Here is the unconstrained formula, and we use the ReLU functions. When the distance is lower than the margin, we don't need to do anything. And if the distance is larger than the margins, it adds linear penalty for it. And it's not that we kept the balancing weight lambda here, the lambda to 0.1 in the experiments, because we want to have the same hyperparameter budget when we're comparing to the previous method. Okay, here's our method. So let's look at our experiments. First, we do the experiments on the standard image classification. Here is our on the right is our solutions. It shows that we got the best calibration performance compared to the baseline and all the previous methods. Here the FLSD is an improved focal loss. It adds some schedule techniques to the lambda. We can surpass all the other methods. And here we also include ones when we just set the margin equal to 0. And here, when we compare this method to the label smoothing and focal loss, they get very similar performance. It validates our insight that label smoothing and focal loss is approximately equivalent to adding a soft penalty of the logit distance equal to 0. And the second table is the accuracy. It shows that our method generally has no cost for the discriminative performance, and sometimes ranking as the best. So it's safe to use it's very safe to use our method. We don't need to to have any cost for the accuracy, but it can have great improvement for the calibration. And for second one is the fine-grained image classification. This task is very challenging for the calibrations because every class is very similar. So it's very hard to get a very good probability for the class. So, but our method is obviously much better than the previous one. It gives a very significant improvement. And here is the experiment to show that label smoothing is very similar, has similar performance to our method when we set the margin to 0. So here we simulatedly improve the balancing weight of label smoothing and the balancing weight in our method. It shows that the trend of the performance is consistent, and they almost get very similar calibration performance. So this further validates our insight that the label smoothing is approximately equal to adding a soft penalty of the equal constraints when we set the margin equal to 0. Here are two evaluation studies on the effect of the margin and the balancing weight. So here on the left, we fix the balancing weight, and we try with different margin to see the effect. We see that it's not very sensitive to the margin, and basically we can set the margin between 5 to 20. And in our experiments, we actually set the model on the CIFAR 10 to be margin equals to 6. And for all the other cases, we just set it to 10. It can give very good results. And on the right, it shows the effect of changing the balancing weight. And we can see these figures. It shows that our method is very robust to this balancing weight. But for the label smoothing, for the label smoothing loss or our loss when the margin is equal to 0, it's not very good to use a large balancing weight. It also validates our insight that the additional term it introduced are trivial or non-information goal. So we must keep the balancing weight very small to get a good result. But for our method, it's much safer to increase the balancing weight because our goal is always a reasonable and informative one. So here are our experiments on two other applications. The first one is semantic segmentation, Pascal VOC 2012. And another one is NLP classification on a data set named 20 news groups. This shows our method, the generalability of our method to handle different situations. So then here are some realizations. Here is the comparison of the reliable diagram, which is realization of the calibrations. We can, if the calibration performance become better, it should be closer to the expected diagonal lines, and our method works a little better than all the others. And here is another very interesting realization. of the segmentation results on the Pascal VOC 2012. And here for first we can look at the we show the reliability calibration visualization for the each sample, and it shows that our method is better. And here for the heat map, the heat map represents the probability or the confidence of the predictions. And if the predictions is higher, the pixel is darker. So for our method work seems very good because it's actually matches our expectations that the model is very confident in the pixels within the object and also outside the object. But for the boundaries, for the pixels on the boundaries, the model is a little uncertain, so it gives a much lower confidence. So this can be a very interesting result. So okay, here is all my presentations. I thank you for your attention, and here I give the link and code our paper. So thank you very much. So any questions?
Hi, Yuan. My name is Matthew Taves.
Hello.
Nice to hear your work. Nice to hear your work. Very interesting, and it's obvious that this calibration is very relevant. I just have a question. Does the result depend on to what degree is the result depending on the distribution of the training data? You know what I'm saying? Like if your testing data has a different distribution than your training data, okay. Are we able to calibrate, according to the prior probability of either the training or the testing data?
You mean the out of distribution experiment?
Mm-hmm. For example, would the result change based on the distribution of either the training or the testing data? How would it change? I guess that's what I meant most interesting.
It's a very important experiment to test on the out of distribution, and I think for we already have some good results on this experiment. I didn't post it on the slide, but okay, I don't know because it's a 3PR submission with in our rebuttal we already have some good results for the out of distribution. Mm-hmm. But maybe I don't think it's very appropriate for post the results now because we're having a public release it. So I can say that our method is also very good for the out of distribution performance.
If I can add something there, Matt, actually, I mean, that's a very good question. And that's the key point of this method. So basically, you work in distribution, that's fine. I mean, you can still be badly calibrated, but the good point is that we can extend that for, out of distribution samples, because there is where you want to have actually the good notion about uncertainty. So it's, let's say you pick a sample from a very different distribution. Is the uncertainty correct or not? I mean, that's a very good question. I can say that all these methods, they focus only on in between or in distribution samples. So we're following the same setting. As being said, after the CPR rebuttal, they were asking also these out of distribution cases. It's not working the same way it works for in distribution, but it's giving very good results. Okay, so I can say it can generalize well. But it's true, I would say the more different the domain shift or the larger the domain shift, you're going to have more troubles. I mean, that's with every method.
I guess it comes down to inductive bias is pretty important, towards your training set.
Yeah, I mean, there are many points to take into account for these cases. So you have this auto distribution. I mean, it's all related because you have this inductive bias. You have, when you talk about auto distribution samples, in this setting, what you want to have like a score that tells you which is the probability of this sample to belong to a different distribution, to one different from the training set. So if you have a well-calibrated network, typically you are going to have a lot of uncertainty, right, in this out of distribution sample, because you learned from a very, I would say, very a close set. So you learn the uncertainty on there. So you are very certain, or you are very well calibrated. And as soon as you get a sample which is very far from your domain, okay, the training domain, is going to have a very high uncertainty score. Okay. So of course it's not perfect, okay, but it is working very nicely in these settings. So I would say, according to the results so far, it's giving also certain out of distribution for calibration. We want to also try what happens in detection. Okay, let's say you have a new sample and you want to see if these samples come from a different distribution. That's some extension you want to do. But I think it's a very good question, actually.
Yeah, and I guess it's not necessarily designed to be optimal for out of distribution. The main gist would be to calibrate according to your in distribution data.
Not directly, but I think that the implication of this is actually implicit, because when you are having some model which is well calibrated, it means that you are going to trust the predictions. So at some point, if something comes where the model is not very sure, it's not very certain, it's going to say, okay, no, stop here. I'm very uncertain about this sample. I haven't seen something like this in my training set, in my closed set. So I'm not willing to give any answer. And that's the point of calibration. So that you can do mistakes. I mean, that's fine. You can still do mistakes. But whenever you are not sure about something, you have a lot of uncertainty. You can say, okay, guys, no, this is a cow and not a tumor, right? So it's something like that. And this is the point of these works.
And I guess there's always susceptibility to adversarial attacks and one pixel attacks and stuff like that too. It's kind of the same thing, I guess.
At the end, it's all related. I mean, you talk about out of distribution, calibration, adversarial. I think it's all related. I mean, you can always fool the network in any case. So it's all related.
All right, thanks. Great work.
Yeah, I think it's a very good direction because I think for the recent calibration papers, they didn't have some very good motivation from the design of their method to handle the domain shift or out of distribution method. And we are also want to test more on this scenario. Yes, and thank you for this session. It's very, very good question.
Yeah, actually, for example, I finished this question is, this temperature scaling. So you get the t-value, you solve the softmax probabilities. This is a state of the, or was a state of the art like 1-2 years ago for doing calibration. This method in domain shift, it totally sucks.
Which method was that? I didn't quite understand. Which method?
This temperature scaling, you have this t-value that when you have the logits, so you have the softmax, right? And when you have the logits, you divide by t. So typically t is equal to 1, so you don't do anything. But if you increase the t-value, you smooth the softmax probabilities, right? And by doing that, you also impose some sort of closeness in the logits. The thing is that this was a state of the art until maybe 1-2 years ago. But in domain shift, this actually sucks, but big time. So
yeah, that makes sense. Did you say Pareto scaling?
Temperature scaling.
Yeah, okay. All right, thanks.
I have a question, Bing.
Okay.
So first of all, thanks for the great talk. It was really, really well made, interesting. So my question is, the methods that you compare against, they have some hyperparameter, right, to control the regularization?
Yeah, sure.
So how did you tune? Yeah, so like the gamma and alpha, for example. How did you tune these hyperparameters exactly?
We follow a very good practice by this paper, by this New Rips 2020 papers for actually follow because they have very good experiment studies. So we'll follow this paper. So in practically the alpha in the label smoothing is set to 0.05 for get good result. And for the focal loss, the lambda is set to about the 3. I set to 3. It's a very standard. It's
Okay.
a very common setting. And for ECP, we tune this one for ECP. I think it's 0.5.
But do you tune it to get the best possible accuracy on the validation set?
For the ECP, I tune it because the previous paper didn't have very good studies. For the label smoothing and the focal loss, we follow the best practice from previous papers.
Okay, but the metric for tuning, is it accuracy or is it calibration?
Yeah, exactly.
Okay.
So being what Christine is asking, if when you look at the validation set and you look at the metric, do you look at the accuracy or do you look at the ECA, for example? That's the question.
I look at the accuracy. I look at the accuracy.
Because if you can go to the calibration plots, I think it's near the end where you compare the different methods.
Which one?
I think you call it reliability plots or the curves at the end. Right here. So here you can see that, for example, for label smoothing and focal loss, you are basically consistently over predicting the confidence in both cases. So probably if you had tuned your parameter, I mean, I sort of understand why you tune this parameter for accuracy, but it's a little bit unfair to say that your method is better at calibration since these methods were not tuned for calibration. In fact, they are uncalibrated right now, like you can tell from the curve. So I'm wondering whether, and did you tune your own parameters, like the margin, was it tuned for accuracy or for calibration or for both?
Let me see. So
the M parameter, was it tuned for calibration?
It's for accuracy. It's for accuracy.
Okay. So for we have a calibrate validation set. So our parameter is tuned for the. I think I tuned for both. Tuned for both accuracy and the calibration.
Okay. So I think you still demonstrate the benefit of your method, but it would be a little bit more fair, I guess, if you had also tuned, and you do it, I think, in one experiment where you tune the alpha to get the best calibration. But
I have this.
Exactly right here. So I guess it would be interesting to see what is the best calibration performance that you can get for these methods, discarding the accuracy performance, I guess.
But back when you do the fine tuning of, I think you optimize only based on accuracy. I don't think you optimize also based on the calibration.
But here,
yeah, I mean here, yeah, but when you go to the older one, yeah.
Oh, sorry. Yeah.
I'm assuming here for M, you are tuned on the calibration because the accuracy doesn't really change, right? So I'm guessing this is.
Yeah. Here, the margin is tuned for calibration.
Yeah.
So also for the label smoothing, it doesn't change as much. Doesn't change much for the accuracy.
But it is for both.
Yeah.
Again, I totally agree with you, Christian. Actually, we have this discussion about what to optimize, and we decided to go with with the literature, because at the end you want to optimize a classification model, and then you want to evaluate when it's, let's say, optimal in classification discriminative tasks, how it performs for calibration, basically. But I agree that to be fair with both, you should have a balance, because at the end you are measuring both. You measure you measure the discriminative performance, but you also measure the calibration.
Or you can do, or you can apply a temperature scaling on all the models so that they're fair.
We did.
So that
we also did that
the
in
curves,
the
you can either shift the curves up or down so that they fit the best possible.
Yeah, we did it also in the rebuttal. We did it, and still we show we have the gap is smaller because with temperature scaling you remove a lot of uncalibration, but still a gap between, let's say, label smoothing, focal loss, and our method.
Nice. Okay. Well, good work.
Okay. Thank you.
Are there any other questions? So maybe I have one more question then. Just out of curiosity, like how does focal loss actually makes the network more calibrated? Because like none of these methods are actually directly optimizing calibration, right? It's just, I guess somebody found out that focal loss helped the network be calibrated, but like, is there any theoretical motivation for this?
I think from intuitive motivations, both label smoothing and focal loss can help prevent the overfitting. Because one potential issue of the miscalibration is the overfitting of the loss. So intuitively, if we look at the formula of the focal loss, it during the training, it lets the training focus more on the samples with lower score, but and as well in the meantime it omits the samples that are already classified very well, and I think that's an intuitive, and from the heuristic motivation. Here is this paper. It shows this link, and this link means that it can help regulate the distribution of the predictions. I think this makes this motivated to a better calibrated model.
And has anyone tried to directly optimize the expected calibration error, like using some sort of a meta learning objective or bi-level objective? I mean, there should be some work that directly optimize calibration, right?
Yeah. Do you mean directly regularizing the probability?
I mean, the ECE,
okay.
For example, the loss. Has anyone tried to directly optimize that in training?
There's one paper.
I think there is this MMCE paper. They do that. They try to optimize directly the ECE.
Mm-hmm.
Yeah,
okay. But they need some sort of validation, double validation set, I guess, something like that.
That paper is the performance of it has a soft the ECE matrix and directly optimize that, but it's not better than the focal loss and the label smoothing.
Oh, really? It's not even better than focal loss. That's
yeah. You can refer to the results in this paper. In this paper, they compare to that method, and it shows that focal loss is a little better than that.
Anyone else has a question? Okay, well, it's a bit late for Bing, so I guess we'll just thank him for the presentation.
Why is it late for Bing? Why is it late for Bing?
He's in China.
Oh,
I'm in China now. Yeah.
He's in China right now.
Side.
Yeah. It's good. So what's your next I mean, maybe what's your next plan? Like, are you extending this? Like, how are you going to go from here?
We hope to, because there's a recent paper, they do a lot of experiments on the new advanced model like a transformer, and in the rebuttal they will also kind of suggest us to evaluate our method on the transformer. So maybe we want to extend it to test it on the more modern networks, because it's evolving so fast. So we need to do that to extend it, and also maybe we want to improve the optimization for the maybe we have idea we don't want to transfer the constraint optimization into a unconstrained formula. Maybe we can try to directly optimize the constraint optimization, which should maybe better, and it can also be hyperparameter free. That can be improvement.
Interesting. Okay, well, thanks again, and hopefully we'll see you in March.
Yeah, I hope so. See you. I hope we can have some physical seminar in someday.
Yeah, we're going toward there. Probably in the summer, I think things will be entirely back to normal if things go well. Okay, so
Okay,
thanks again,
great.
and we'll see each other in 2 weeks for the next seminar.
Thank you.
Thank
you.
Bye-bye.
Bye.
Bye.